Unit 4, Lesson 1, Trigonomic Ratios on an XY plane. So in the previous lesson, we started putting angles on an XY graph, which is called the Cartesian plane. We learned a lot of the terminology, so we learned what it means to have an angle in standard position, we learned what the initial arm was, and we learned what the terminal arm was. So putting angles on our Cartesian grid or an XY plane is great, because if we're given a point, we can actually generate a terminal arm, right? If I told you that point 2, 3 is on the terminal arm of an angle drawn on an XY plane, it's very easy to replicate that angle. So all you would do is you would, on your graph, you'd find point 2 and 3, and then since it said in the question, that point is on the terminal arm, you draw your terminal arm. You know that this is at 2 and 3. Okay, you know your initial arm is on the positive x-axis, so your angle would be in between those two arms. Okay, and we're going to get into this in a little bit more detail, but just know that this is the direction we're headed with this lesson. So example 1, the terminal arm of angle theta in standard position goes through the point √3/1. Part A, draw the scenario above and create a fully labeled right triangle. So we'll have to use Pythagorean theorem to find one of the sides. Okay, so for part A, we're going to draw this scenario. So let's plot that point on the grid. So √3/1 is going to be in quadrant 1. And we know that that point is on the terminal arm. So let's draw the terminal arm. Okay, now we can generate a right angled triangle by drawing a line straight down from that point to the x-axis. Okay, and now using our terminal arm, our initial arm, and that dotted line, we form a right triangle. So since we know that point is at √3/1, we know that this side of the right triangle is √3, and this side of the triangle is 1, right? Because √3 in the point is our x value, so that's the value of the side of the triangle that is generated from the x-axis, and the y value of our point is 1, so that's the side length of our vertical side. Let's finish labeling this triangle by finding out the length of the hypotenuse. So let's do Pythagorean theorem to find out that length. Okay, so we know that the hypotenuse has a length of 2 units. Okay, so we're done part A. We've drawn out this scenario, created a right triangle, and labeled all of the sides. Part B says determine the sine of theta, cos of theta, and tan of theta. Remember, theta is the angle that's formed between the initial and terminal arms. Let's go ahead and find those ratios. So sine of theta is opposite over hypotenuse. So sine of theta is going to be 1/2. Cos of theta is adjacent over hypotenuse, so cos theta is going to be √3/2, and tan of theta is opposite over adjacent, so tan of theta is going to be equal to 1/√3. Okay, so there's all our ratios, so that's part B complete. Now part C says actually solve for theta. So to solve for theta, usually you would go ahead and isolate for theta, so you'd go theta is equal to sine inverse 1/2. And then you'd plug that into your calculator and get your value of theta. And that's usually what you're going to do. However, this is a special triangle. Okay, I'm going to redraw it over here, and maybe that will spark your memory of this special triangle. Okay, so I've just drawn the special triangle that you need to use to solve for theta. So we could use any one of these ratios, because we're solving for essentially that related acute angle. Okay, and the related acute angle is always going to be positive, because that related acute angle is always in quadrant 1. Okay, so any one of these ratios can be used to find theta. So if I take, let's say I'm going to use sine theta equals 1/2, I'm going to go to my special triangle to solve for theta. So remember, sine is opposite over hypotenuse. Okay, so which angle has an opposite side of 1 and a hypotenuse side of 2? Well, that's 30 degrees, right? So therefore, theta must be 30 degrees. Okay, and we just got that using our special triangle. If this triangle had dimensions that did not reflect a special triangle, like let's say this was 1.5, this was 6.2, okay, that's not a special triangle. So then you would just solve using regular methods. You would do theta equals sine inverse times 1/2. Okay, you only use special triangles when it is a special triangle. Okay, I'd like you guys to pause the video and read through this table. But basically all this chart is showing you is that now that we know how to generate an angle when you're given a point and a terminal arm that goes through that point, it's really easy to come up with the lengths of the opposite, adjacent, and hypotenuse side just from that point value. Okay, so we realized in the last example that your x value of the point is the same as your adjacent side. We also saw that your y value of the point is the length of the opposite side. And then finally, to find your hypotenuse side, you're going to use Pythagorean theorem. And the reason why I want to point this out is because in future, if ever you get a question where you're given a point on a terminal arm and asked to come up with your sine, cos, and tan ratios, you don't necessarily have to draw the triangle out. If you know that x is equal to adjacent, y is equal to opposite, and then you can calculate your hypotenuse by using Pythagorean theorem, so we'll call that side r is equal to hypotenuse, we can actually regenerate the equation sine, cos, and tan in SOHCAHTOA using these values. And instead of saying sine is opposite over hypotenuse, right, because that's really great when you have a triangle, we could actually say that sine is equal to y over r. It's the same as opposite over hypotenuse, just the y and the r refer to the point. So this is just another way of writing those trig ratios, and they're really helpful to use when you're given a point. Okay, because you don't actually have to draw out the triangle. As long as you know the x value of the point and the y value of the point, and you can plug those into Pythagorean theorem to get your r value, you can then generate each of these equations. Okay, example 2. For each angle, sketch out the principal angle, then sketch the related acute angle, and then determine sine, cos, and tan on your calculator. Okay, so the first one, theta equals 30 degrees. Let's go ahead and sketch that. Okay, so there's my principal angle. Now remember, the related acute angle is the acute angle that is formed between the terminal arm and the x-axis. So in this case, our related acute angle is the same as our principal angle. And remember, related acute angle is denoted as beta. Okay, now let's go ahead and find the value of sine, cos, and tan 30 degrees. And those are the values that you get when you plug them into your calculator. Okay, let's sketch 150 degrees on the second axis. Okay, so there's our principal angle. Part B, let's go ahead and find our related acute angle, which is right there. So related acute angle is going to be 180 degrees minus 150 degrees because our terminal arm is in quadrant 2. So our related acute angle is 30 degrees. Now let's go ahead and calculate the sine, cos, and tan of 150. And you're going to get values very similar to what we got in part A, just some are different in terms of their negative or positive sign. Okay, let's go ahead and sketch our principal angle of 210. There it is, there's our principal angle, and now our related acute angle is going to be in there, so let's calculate that. So our related acute angle is going to be our principal angle minus 180 degrees. And we're going to get 30 degrees. Now let's calculate the sine, cos, and tan of 210 degrees. And again, we get similar answers, just some differences in terms of the answer is negative or positive. And let's pull out our last one. There's our principal angle of 330. Our value of our related acute angle is going to be 360 degrees minus 330 degrees because it's in quadrant 4. So our related acute angle is also 30 degrees. Okay, let's calculate the sine, cos, and tan of 330. And there's the values of each ratio. Okay, so we see some similarities here, right? When we took sine of 30, sine of 150, sine of 210, sine of 330, we got 0.5 in every case. Just sometimes it was negative, sometimes it was positive. Same thing with cos of 30, cos of 150, cos of 210, cos of 330. We always got 0.87, just sometimes it was negative and positive. And we notice the same trend for the tangent ratios, okay? And the reason why is because in each of these 4 examples, the related acute angle was always 30, okay? And that's the reason why the numerical values of our ratios were always the same, okay? They all have the same related acute angle. The next thing I want you to look at is what do you notice about the sign of each of the ratios when the terminal arm is in each of the 4 quadrants, okay? So let's look at that. In this first example here, the terminal arm is in quadrant 1, okay? and every ratio is positive. Those are all positive numbers. So let's write that down. So when the terminal arm is in quadrant 1, sine, cos, and tan are all positive. When the terminal arm is in quadrant 2, only sine is positive. The rest are negative. When the terminal arm is in quadrant 3, only tan is positive. And finally, when the terminal arm is in quadrant 4, only cosine is positive. And the part of this lesson was just to essentially create a rule that we're going to use in future lessons. And that is called the Castor Rule. So the Castor Rule tells us which ratios are positive in a given quadrant, and this is important. So remember, our quadrants are labeled this way: 1, 2, 3, 4. Okay? So in quadrant 1, all of the ratios will be positive. Sine, cos, and tan will all be positive. We saw that right here. This was an example of when the arm was in quadrant 1 and each sine, cos, and tan were positive. Castor Rule tells us that in quadrant 2, only sine is positive. When we go back up here, look, arm is in quadrant 2 and only sine is positive. Okay, this trend continues. So the Castor Rule tells us that in quadrant 3, only tan will be positive, and in quadrant 4, only cosine will be positive. You might not really understand what this is used for yet, but right now I want you to memorize the Castor Rule. Castor Rule tells you which ratio will be positive in a given quadrant. Okay, so let's put this into a bit of action. So example 3, sketch theta equals 280, and then we have to determine a few things. So let's go ahead and sketch that. Okay, so there is 280 degrees in standard position. Let's determine the following 3 things. So A, which quadrant does the terminal arm lie in? Okay, well, our terminal arm is in quadrant 4. Part B says, figure out the value of the related acute angle. Well, the related acute angle is between the terminal arm and the x-axis, so it's right here. So it's going to be equal to 360 degrees minus the principal angle, so 280 degrees. So that means that the value of our related acute angle is going to be 80 degrees. Okay, and part C says, figure out the values of sine, cos, and tan 280. Okay, so when you plug them into your calculator, that's what you get. And now let's compare this to the Castor Rule that we just learned. So, our terminal arm is in quadrant 4. Okay, the Castor Rule tells us that in quadrant 4, cosine is the only one that should be positive. Did that happen? Yes, cosine was the only one that was positive. The other 2 were negative. So this is all very introductory. You're probably not seeing what the point of this is yet, but just wait till our next few lessons. Okay, get comfortable with the connection between Castor Rule and the sign of the ratio, if it's negative or positive. And then in the next few lessons, we're really going to put it into play, and you're going to be like, oh, that makes sense why we need to be able to do this. Example 4, use the related acute angle to state an equivalent expression for each ratio. So we need to come up with something that is equal to sine 120. So the first thing you want to do is draw out the rotational angle. So the rotational angle is the one in question. So we're going to draw out 120 degrees. Okay, so there's our rotational angle of 120 degrees. Let's focus on that terminal arm. Okay, so we're in quadrant 2. Is sine positive or negative in quadrant 2? Well, you want to look at the Castor Rule, C-A-S-T. In quadrant 2, the Castor Rule tells us that sine is the only ratio that's positive. Okay, so in this quadrant, the one where our terminal arm ended up, sine is positive. That's really important. Okay, so we realize that sine is positive in quadrant 2. So to create an equivalent expression, we need to ask ourselves, which other quadrant is sine also positive in? Let's go back to our Castor Rule. In quadrant 1, all of the ratios are positive, so that would include sine. So the answer here is sine is also positive in quadrant 1. So that means we can create an equivalent expression using the angle in quadrant 1. Okay, so we're going to take our related acute angle from our original angle, so that's 60. Right, I just took 180 and subtracted the principal angle. And we're going to draw an angle with the same related acute angle in quadrant 1. And there it is. So therefore, we can conclude that sine of 120 degrees is going to be equivalent to sine of 60 degrees. You can check your answer using a calculator. Type in sine of 120, it's going to be the same as sine of 60. Okay, that might be a little tricky for some of you still, so let's try another example. So find an equivalent expression for tan of 290. Well, let's follow the exact same steps. So first, let's draw our rotational angle. Okay, so there's our rotational angle, and we can stick in that related acute angle. So our related acute angle here is going to be 70 degrees. Right, just do 360 minus 290. Okay, so step 1 is done. Step 2 is determine if tan is positive or negative in that quadrant where the terminal arm ended up. Okay, so the terminal arm ended up in quadrant 4, and because of the Castor Rule, tan is negative in quadrant 4. So, to generate an equivalent expression, we need to create an angle with the same related acute angle in the quadrant where tan is also negative. So look at the Castor Rule. Which quadrant is tan also negative in? Okay, well it's positive here, and they're all positive there. So it's also negative in quadrant 2. So I'm going to generate an angle in quadrant 2 with the same related acute angle of 70 degrees. Okay, so there's a related acute angle of 70 degrees. Terminal arm is in quadrant 2, because that's where tan is also negative. Now let's calculate the value of that principal angle. So it's going to be 180 degrees minus the related acute angle. Okay, so therefore, an equivalent expression would be tan of 290 is equal to tan of 110. Okay, tan is negative in both quadrant 4 and quadrant 2. They both have the same related acute angle. Okay, that's how we're generating this expression.